Okay, guys, welcome to another video. This is the complete A2 Physics Guide Part 3. Now, Part 3 and Part 4 mainly consists of the final four chapters, which are quantum physics, nuclear physics, astronomy and cosmology, and medical physics. Part 4 is all of medical physics because that in itself is the single largest chapter in our A2 syllabus. So, before we start, I'd like to address some changes that I'm going to be making. So, first of all, I got a very good feedback from one of my viewers. That is, my videos are usually long because I tend to write the chapter name, then I go over the definitions and the repeated short and long SAQs that have arrived in the last 20 years. So what I did was I used to just write them while talking to you guys, but that took a lot of time. So what I've just done is I have already written down the major, all of the definitions and the previous past paper questions and answers, which I will be going through at a faster pace with you guys since I don't have to write anymore. What I will instead be doing is in the video, I will be explaining you guys the concept as I write it down because when I'm explaining the concept, you guys should understand what my thought process is. Okay, so let's get started. This is the entire file that we'll be going through. Hopefully, we can finish it within a small amount of time. But yes, otherwise, let's start. Okay, so nuclear physics, so quantum physics. So in quantum physics, we have the definition of a photon, which is quantum of energy of electromagnetic radiation, the work function energy, which is minimum energy of a photon to cause emission of an electron from a surface. Wave nature of matter is electron diffraction. Then explain how the emission spectrum provides evidence for the existence of discrete energy levels for the electron in a hydrogen atom. So we can say that proton energy is equals to difference in energy levels. Energy of a photon has corresponding frequencies or wavelength. The spectrum shows discrete frequencies or wavelengths, so energy levels of electrons must also be discrete. Now, particle nature of electromagnetic radiation is the photoelectric effect. Evidence for photoelectric effect is can be described as okay. So this is written in bullet points, which are threshold frequency, rate of emission is proportional to intensity, max kinetic energy is independent of intensity and dependent on frequency, no time delay between illumination and emission. Then we have the definition of photoelectric effect, which is electromagnetic radiation incident on a surface causes emission of electrons from the surface. Definition of de Broglie wavelength, which is wavelength associated with a moving particle. Then we have the definition of threshold frequency, that is the lowest frequency of electromagnetic radiation, giving rise to emission of electrons from the surface. Number 10 is a question saying phenomena associated with photoelectric effect that cannot be explained using wave theory of light. So basically what this question tells you is to write some points which you can explain with photoelectric effect, but you cannot explain with wave theory of light. So that is, we can say that instantaneous emission of electrons. Again, max kinetic energy depends on frequency, does not depend on intensity. Threshold frequency. You will see that question number 10 is very similar to question number 6, but the phrasing is different. Therefore, I've written it in case just not to miss it. Okay. Okay, moving on. We have state appearance of visible line emission spectrum as seen using a diffraction grating, that is colored lines and mostly dark. Then the definition of threshold wavelength is highest wavelength of electromagnetic radiation giving rise to emission of electrons from the surface. This is because energy is proportional to uh, energy is proportional to wavelength, inversely proportional to frequency. All right. Okay, then they have told us to describe the absorption line spectra, We can say electrons in the lower energy state absorb photons. Energy of a photon is equal to the difference in energy levels. The electrons excite and subsequently de-excite, thus emitting the photons in all directions, which appear as black lines. Question 13 is a combination of question number 11 and question number 4. So that's that. I think these so this is the compilation from 2009 to 2024. Oh, sorry, 2025. So that's that. Now let's delve into the concepts of quantum physics. Now, the main concept is, the main thing that we deal in quantum physics is with photons. So our first concept is energy of photons. So what's the energy of photons? Energy of photons is proportional to frequency. So we can say E is equals to HF, where H is a constant. Okay, all right. Now we also knew velocity is F lambda, velocity of a wave. Okay, so we can say frequency is equals to V by lambda. So velocity of light is denoted as C. Therefore, our final equation, I mean, we can also use this one, but most of the time we use E is equals to hc by lambda. This is another equation where E is energy of photon, energy of photon. The unit is electron volts. Okay. The Okay, something that's funny is you will learn the conversion from joule to electron volts in the chapter nuclear physics, but for now you just have to know this, okay? All right. Okay. C is the speed of light. Speed of light. Unit is meter per second. F is equals to the frequency, which is unit is hertz. Uh, and h is the Planck's constant. That is 6.63 times 10 to the power minus 34 joules second. Okay, uh, just for you guys, what I'll do is I'll just write down I won't show you guys the conversion, I'll just write the value. That is 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. Okay? All right. Nice. Okay, so next. Okay. Now, next concept is, the secondary concept is uh relation between photon energy, work function, and Ke. Work function and Ke. Okay. All right. So, first of all, let's just I have to note this down that if energy of photon greater than threshold, sorry, is greater than work function, is greater than work function energy, then frequency is greater or equal to threshold frequency. Actually, it's greater, but sometimes it can be equal as well. Okay, so how do you represent this? So energy of photon equals to work function energy plus maximum kinetic energy of electron. So E is equals to psi plus Ke max. Now we can also write E is equals to HF as we learned in the first concept. Psi is represented as psi, and we can write Ke max as Ek max. Okay, therefore this is okay. Therefore, we can say it is equals to Hc by lambda. Hc by lambda is equals to psi plus Ek max. Right. Now, what's the work function energy? Okay. The work function energy, psi, is equals to Planck's constant multiplied by the threshold frequency. Wait. Sorry. This is actually the third concept. That is work function energy. If you guys don't remember what that is, it is the minimum energy required to remove an electron from the surface or cause emission of an electron from surface. So the work function energy has two formulas, which is HF naught slash psi is equals to HC del naught, where, wait, let's write them down, where psi is equals to, right, where psi is equals to work function energy, function energy, H is equals to Planck's constant, 6.63 10 to the power minus 34 joule per second. Oh, sorry, joule second. Right. C is equals to speed of light. Meter per second. F naught is the threshold frequency, and lambda naught is the threshold wavelength. All right, nice. Okay, next. What space do we have? We have, I think, space for two more concepts, then you have to switch it to the right. Okay. Next concept is momentum of a photon. Momentum of a photon. So, momentum, we know mv is equals to h lambda, sorry, h by lambda is equals to h by lambda. H is equals to p into lambda. This is equation 1. All right, then we know P is equals to hc by lambda is equals to h, Sorry. We know that h is equals to p into lambda, right? Which is p into lambda into c by lambda, lambda cross. Therefore, energy is equals to momentum into speed of light. Momentum is equals to energy by speed of light. So this is one way to think about it, but I want to give you guys another prospect. Okay. Now, some of you guys might feel a little confused here, but I'll try to break it down even further. Just label this as breakdown. Okay. All right. So as I said, let's repeat. MV we know is h by lambda. Okay. All right. Let's look through draw two lines here. So we can say lambda is equals to, and say lambda is equals to h by p because mv is equals to momentum. Now here we know energy is equals to hc by lambda. Lambda is equals to hc by e. Now if we excuse me. Now using now let's equate lambda is equals to lambda. Then we can say hc by e is equals to h by p. H cancels out, which gives us P is equals to E by C. Unit kg meter per second. Simple. Because it's momentum, right? Nice. Okay. Next is calculation of intensity. This was for calculating intensity. So this is a formula that I did see once in 15 years. It never came after 2022 or even after 2015 when I'm still writing it down. That is, intensity is equals to energy divided by area into time, where intensity is proportional to energy. Nice. Nice and easy. Okay, now, since it's proportional to energy, this very same energy has another, this energy also has a formula. That is energy equals to number of photons multiplied by energy of each photon. So this is actually the total energy. Okay, this is the total energy. All right. Okay. I think I should have mentioned a few things where P is equals to momentum, C is speed of light, E is energy of photon. Make sure to write this down as many chances as you get so that you don't forget the unit or the constants. So that is 3 into 10 to the power 8 meter per second. And this is, sorry, it's just unit, right? It's electron volts. Okay, now moving on to 6. 6. So this is regarding line spectrum. Line spectrum. Okay, so we have two types of line spectrum. One is the emission line spectrum. Okay, the emission line spectrum deals with a cloud of hot gas. Okay, yeah, and the line usually looks like this. This is 1, this is 2, this is 3, this is 4, and finally this is 5. Right. Okay. Now, you draw it first and then I'll explain. This is 1. This is 1. This is 1. And this is 1. Okay. Uh, okay. Where? Let's say this is the nucleus. Consider this line as the electron shells. This is actually a hydrogen atom. Okay. Minus 3.41. Minus 1.51. Minus 0.85. Minus 0.55. Minus 0.38. Now, you are usually told to find the photon's energy uh, using these lines. Okay, so because the photon energy correspond with the frequency or the wavelengths that is given. So basically the change. All right. So we can say photons energy is equal. So let's take this one. Let's take the largest one. Let's find this photon. Okay, let's find this photon. Okay, this one. A photon's energy is equals to 3.41 minus 0.38 is equals to 3.03 electron volts. It's an example. So now, now, as we know that E is equals to HF or comma E is equals to hc by lambda, we can say we can say E1 minus E2 is equals to HF, right? Because the change in the energies is the energy of photon. Okay. the large value, the small value. You guys can ignore the minus, by the way. But if you include the minus, then just make it opposite. For example, for example, let's say let's say let's take these values, 3.41 and 0. Let's take these values, right? So 3.41, 0.38. We got 3.03. Now, if you take the values without the minus, then you'll get 3.03. But there's one more way to do this. If you include the minus, minus 0.38 minus 3.41, which is equals to minus 0.38 plus 3.41, which also equates to 3.41 minus 0.38, which is equals to 3.03 electron volts. So, yeah, depends on if you include the signs or not. Okay. Now, what we can do is we can further take this example and we can find out usually the wavelength uh, of we can find out the wavelength of the photon that was emitted by the electron as they de-excite. Okay, so that would be 3.03 times 1.6 times 10 to the power minus 19 is equals to 6.63 times 10 to the power minus 34 times 3 into 10 to the power 8 by lambda. Therefore, lambda is equals to 4.1 times 10 to the power minus 7 meters, which is usually blue slash violet light. Right. Then we have the absorption line spectrum. Absorption line spectrum. Okay. The absorption line spectrum is actually a white of cool gas, sorry, is a cloud of cool gas. Cloud of cool gas through which white light passes. All right, so white light goes through here. Again, we just have to draw um the same diagram as for the emission spectrum. 1, 2, 3, yeah, 4. Check this is what's wrong. 4, and finally 5. Right. Okay. So let's just draw some frequency. Let's just draw some absorptions. 1, 4, 1, 2, 3, 4, 5. Right. Oh, we have one from this one. This is 2. Actually, I'd like to draw with the other color. This is 1. I got it. So let's say this is 1. Uh, this is 2. This is 3. This is 4. So one of this here, and another one goes from. Okay, my drawings are absolutely so bad. They're so terrible. Why is it hard drawing arrows from top to bottom? From bottom to top. And finally, one should be here. Okay, now, same values as before. Again, because this is the nucleus, minus 3.41, minus 1.51, minus 0.85, minus 0.55, minus 0.38. This is energy, electron volts. Right. Same concept as before, same way of calculating energy as before. Now, how to calculate the energy for this one? Simple. That is for this one, feel like, oh, okay. For this one, since it's going top, so final minus initial, right? So you can say minus 1.51 minus 3.41. Right, that's how you do it. Okay. Okay, right. Okay, which is equals to same. Oh, sorry, let's take the previous example as before. Basically, the energies are supposed to be of the same value. Okay, they're supposed to be of the same value. Now, if you take the largest line, uh, let's draw another line that is let's say final minus 0.38 minus 3.41 is equals to minus 0.38 plus 3.41, which is equals to 3.03 electron volts. So it's the same calculation as before. So you guys don't have to sweat it. All right. How much space do we have? Oh, we still have a lot of space. Okay, I think I can work with de Broglie wavelength, our next concept. So concept number 7 is de Broglie wavelength. See, this is the wavelength associated with a moving particle. All right. So we know E is equals to mc square and E is equals to hc by lambda. We can equate the energies and write mc square is equals to hc by lambda. Cancel out the, so we get mc is equals to h by lambda. We can also say hc is momentum. So P is equals to h by lambda, lambda is equals to h by p, where unit is meters. Unit meters. Where lambda is equals to wavelength, which is equals to Planck's constant, which is 6.63 times 10 to the power minus 34 joule second, and B equals to momentum. It is equals to, oh, yeah, momentum, kg meter per second. Right. So that's that. Okay. These are all of the concepts that are required for your the major concepts at least. There are some space case specific concepts for for quantum physics, but you do not need them because that those never came after 2011 or 12. However, if I were to add one more thing, that would be number 8, important wavelengths. Right. This is the one thing that I would add. Okay. So you have number 1, blue light, which is 380 to 500 nanometers. By the way, nanometers is equals to 10 to the power minus 9. 2 is red light, which is 620 to 700 nanometers. 3 is ultraviolet, which is 100 to 400 nanometers. 4 is X. So, as I was saying, you also have to know the wavelength of X-rays, which is around, wait, I forget. I think it was 0.1 to 1 nanometer. I'd have to check. I think I forgot. Sorry, so it was 0.01 to 10 nanometers is X-ray. So the reason you're supposed to know this is because the question might ask you to find the wavelength, and then it might tell you that under which spectrum does it fall. So you have to say if it's a blue light, red light, ultraviolet, or X-ray. So yeah, that's all for our quantum physics. Now let's move on to nuclear physics, chapter 12. So in nuclear physics, we have mostly definitions and a few conceptual questions. Number 1 is radioactive decay constant. It is the probability of decay of a nucleus per unit time. Isotopes, nuclei having the same number of protons but different number of neutrons. Nuclear fusion reactions of two light nuclei combine to form a more massive nuclei. Nuclear binding energy, minimum energy needed to separate nucleons in a nucleus to infinity. Radioactive decay, the random and spontaneous emission of alpha particles, beta particles, and gamma ray photons from a particles. Never say gamma particles, okay? Always gamma ray photons. Gamma particles was accepted in IGCSE O levels, but will not be accepted in A levels. Nucleus is central part of a central part of an atom. Nucleons is proton or neutron contained within the nucleus. Gamma radiation is photons of electromagnetic radiation emitted from nuclei. Radioactive is random and spontaneous emission of particles from unstable nucleus. Nuclear fission is a single large nucleus divides to form a smaller nuclei. Um, 11 is the energy released from fusion or fusion reactions is the kinetic energy, and number 2 is energy of gamma ray photons. Mass defect is the difference between mass of nucleus and the mass of constituent nucleons, where nucleons are separated to infinity. Spontaneous decay is the decay of nucleus not affected by environmental factors. Radioactive half-life is the time for activity or number of nuclei of sample to become half of its initial value. Random decay is time at which nucleus will decay is unpredictable, or I think the recent key statement is cannot be predicted. This is the recent more This is the better thing to say, cannot be predicted. Anyways, reasons why sample is not equal to measured count rate. Number one, sample emits in all direction, but detector captures in one direction. Background radiation. Some emissions absorbed before reaching detector. Death time of counter. Daughter nucleus is unstable. Do you guys know what daughter nucleus is? Daughter nucleus is, let's say, uranium. Okay. Or let's say, okay, not uranium. Let's say an unstable nucleus that has given out alpha particle or beta particle or gamma ray photon, and it turns into a new nucleus with a different number of uh, proton and neutron. Now, the thing is, this nucleus can also be unstable, and this nucleus is called daughter nucleus. Okay, so that's all you have to know. Then activity is number of nuclear disintegrations per unit time, and tracer is a material introduced into the body and absorbed by the tissues that is being studied. Okay, I think I made a mistake. Okay, that's right. Anyways, let's go into the concepts of nuclear physics. I think nuclear physics does not have that many concepts, so we should be able to do this fast. Okay, all right, all right. So nuclear physics. The number one is universal equation. Okay, the universal equation for nuclear physics is E is equals to mc square, where E is equals to energy, m is equals to mass, c is equals to speed of light. All right. Now, in this chapter, you're required to know the conversion of electron volts to joules. Okay. Two is EV to joules plus joules to EV. Now, we know that 1 electron volt is equals to 1.6 times 10 to the power minus 19 joules. Therefore, 1 joules is equals to 6.25 times 10 to the power 18 electron volts. And 1 U refers to unified atomic mass unit, is 931 mega electron volts. This is very important. Memorize this. Okay, now our third concept is, sorry, our third concept is mass defect. That is, mass defect is equals to mass of reactants minus mass of products. Mass of products, which can be said as del M is equals to Rm minus Pm. Okay. Now, number four, binding energy. This is mainly the place where we use our formula from concept number one. So binding energy is calculated using E is equals to del mc square, where del m is the mass defect. Okay, then we have something, then binding energy, then we have binding energy per nucleon, per nucleon, which is equals to the binding energy divided by the number of nucleons. One thing to note here is more binding energy per nucleon, uh, more stable nucleus. Right, moving on. So, oh, wait, excuse me, hold up. Okay, there is some notes that I want to include for mass defect. That is mass defect of products is always less than mass defect of reactants, uh, and that also mass of products is less than mass of reactants. Nice. All right. So our next concept is particle energy. Particle energy. Okay. Particle energy is if 1 mole of X is 1500 joules, then 6.02 times 10 to the power 23 particles of X has 1500 joules. Therefore, one particle of X has 1500 divided by 6.02 times 10 to the power 23. Okay, therefore we can say it is the energy released by one particle of an element. Right. There's one thing more to note. We note energy released in reaction is equals to binding energy of products minus reactants. This can also be written as Q is equals to energy of products minus energy of reactants. Okay, nice. Then this was our fifth concept, right? And now moving on to our sixth concept, that is radioactive decay. Okay, so decay constant is equals to probability divided by time. So decay constant is denoted with lambda del n by n divided by del t. Uh, we can write del n by del t. Sorry, del t times n. So del t and del n is equals to activity. So you can say activity divided by n. Therefore, you can say A is equals to lambda n. Now, where, okay, w- where A is activity, the unit is BQ. BQ is becquerels. It's a very niche unit, so make sure to remember it. Becquerels. Becquerels. Lambda is equals to decay constant. Um, per second, unit is per second. And finally, N is number of undecayed nuclei. Nice. Okay, right. So our next concept. Okay, I think we have almost two more concepts. Major two for calculation in this chapter. Can I reduce the size and uh okay, no worries. I think I'll make it work somehow. So number wait, which one was this? Number six, number seven. Right. Number seven is exponential function decay. Potential decay of activity nuclei and count rate. Okay, so activity is equals to A naught e to the power minus lambda t. N is equals to N naught e to the power minus lambda t. And R is equals to R naught e to the power minus lambda t. It's the general equation. Okay, where A is final activity, A naught initial activity is equals to, oh, actually I can write this in a better way. So the, we can say that the general equation is x is equals to x naught e to the power minus lambda t. This is just like discharging of the capacitance formula. Okay, so we can say So we can say where x final value of activity uh n- nuclei, okay, whatever, x is equals to activity final value, x naught is equals to initial value, uh lambda is equals to decay constant, t is equals to time, m is equals to final m is equals to number of nuclei, r is equals to count rate, and finally a is equals to activity, which is becquerels. Nice. One more concept is left, that is half-life. Half-life. So we know that from concept number 7 we learned n is equals to n naught e to the power minus lambda t. Now if t is equals to t half, n is equals to n naught by 2. So we can say, so n naught by 2 is equals to n naught e to the power minus lambda t half. N naught cancels out. E to the power minus lambda t half is equals to half. Uh, is equals to lambda t half is equals to 2. Lambda t half is equals to ln 2. Therefore, half-life is equals to ln 2 by, sorry, my bad. So therefore, lambda is equals to ln 2 by t half, which is equals to 0.693 divided by t half. You can use either ln 2 or 0.693, however you wish. Okay, nice. If it were me, of course, I would always keep it as ln 2 because that's more accurate. Finally, so we're done with our nuclear physics. Was nice. Now moving on to astronomy and cosmology. This is very new. This came after 2022, so there are not many questions, and the concept part is also very small. There's only just a few countable formulas. So, chapter 13, astronomy and cosmology. Number one, we have luminosity of a star, that is total power radiated by the star. Explain how standard candle in a distant galaxy can be used to determine the distance of the galaxy from the observer. Standard candle has known luminosity, radiant flux intensity measured by observer, and distance calculated using F is equals to L divided by 4 pi d square. State Hubble's law is velocity is proportional to d, where v is speed of precession of galaxy from an observer, and d is the distance of the galaxy from the observer. Explain why the wavelength observed of the Earth is different from the wavelength that the galaxy is known to have. This is because galaxy is moving away from the Earth. Wavelength of light from the galaxy is increased due to redshift. State Wayne's displacement law using symbols. Lambda is in proportion is inversely proportional to t, where lambda is wavelength at peak intensity observed from the star, and t is thermodynamic temperature. State the name of the phenomenon that gives rise to the change in wavelength. It's redshift. Then, what does redshift show about the motion of the galaxy moving away from the observer? Standard candle, astronomical object with known luminosity. State Wien's displacement. This is without symbol. You have to say that wavelength at peak intensity is inversely proportional to thermodynamic temperature. Then, what is meant by redshift? Apparent wavelength is greater than known value due to movement of star away from the observer. Okay, then how the surface temperature of distant star may be determined from the wavelength spectrum of the light from the star. So we can say that wavelength at peak intensity of distant star is determined. Wavelength at peak intensity from object of known temperature is determined. Hence, Wien's displacement law is used. And number 12 is how cosmologists use observation of emission spectra from stars in distant galaxies to determine that the universe is expanding. We can say that you have to say that wavelength of spectral lines are greater than their known values. Redshift shows stars in distant galaxies moving away from the Earth. Number 13, why the radiation from the star is redshifted. The star is moving away from the observer. Number 14 is how cosmologists determine that the light from a distant star has undergone redshift. So we can say that by examining the lines in the spectrum of the light from the star and comparing with known spectrum. Finally, explain how Hubble's law and the idea of the expanding universe led to the Big Bang theory of the origin of the universe. So you have to say that all parts of the universe are moving away from each other. More distant objects are moving away faster, so everything must have been closer together at a single point. Right. Okay. Now for the concepts. Okay. Number one. So let's calculation of luminosity. This is the total power radiated by the star. Okay. That is radiant flux intensity is equals to um luminosity by surface area. Surface area. So L divided by A, where L divided by 4 pi r square, or 4r L divided by 4 pi d square. L divided by 4 pi d square. Okay. Therefore, F is equals to L divided by 4 pi d square is the formula where unit is watt per meter square. Now, the idea is that, let's say this is a galaxy. Let's say this is a star. This is the star's orbit. There is a distant galaxy in this direction. Let's make the star bigger. Okay, now the light of the star is going in all directions. All right. And it's also going here, and the distance is d. Okay. Now, surface area of galaxy is equals to 4 pi d square. Nice. Okay. So that is the concept. Number two is laws applied on a black body. Laws applied on a black body. That is. Okay, guys. So the laws applied on a black body is the um Stephen Boltzmann law, where luminosity is proportional to surface area, and luminosity is also proportional to thermodynamic temperature. If we combine them, you can say that luminosity is proportional to area multiplied by thermodynamic temperature, which in turn gives us the formula luminosity is equals to Stephen Boltzmann constant multiplied by surface area multiplied by thermodynamic temperature to the power of 4. Right. So as these are the denotations where A is equals to surface area of star, meter square, L is luminosity in watt, T is surface temperature in Kelvin, and This is Stefan Boltzmann constant, which is 5.67 times 10 to the power minus 8. Okay, right. Excuse me, give me a moment. So, which is the watt per meter squared to the times temperature to the power minus 4. Oh, sorry, Kelvin to the power minus 4. Sorry. Plus K to the power minus 4. Nice. Okay. Uh, Next. B is we draw a graph. Right. Nice. So this is luminosity per watt, temperature in Kelvin. Right. This is 0. This is a real body. And this is the graph of a black body. Of a black body. Now, for two stars of the same luminosity, surface area is 1 by 2 to the power 4. We know luminosity's formula is A t to the power 4. We can say L by this is A t to the power 4. Hence, we can write A A1 T1 to the power 4, A2 T to the power 4. Right. Then as A is equals to 4 pi d square. No, as A is equals to oh okay. As A is equals to 4 pi r square, or A is equals to pi d square, we can say that root of d1 to the power 4 to d2 to the power 4 d1 square d2 square. Therefore, I can come up with the formula d1 t1 square is equals to d2 t2 square. But most of the time, I think this is the main formula. This is just the main formula. This is an extension of what is in your book. The syllabus doesn't explicitly tell me to mention this, but I still did just in case. Okay, next. Finally, concept number 3 is Wien's displacement law. Or Wien's displacement law, as some may say. So Wien's displacement law is wavelength at max intensity is proportional to 1 by thermodynamic temperature. So lambda max T is equals to constant. Therefore, we can say lambda 1 T1 is equals to lambda 2 T2. Next concept is redshift. Or redshift is change in wavelength by the given wavelength B divided by C. Okay, or can also go for change in frequency. There are like two formats. Change in frequency by frequency is equals to V by C. If velocity increases, velocity is proportional to lambda, so velocity increases, lambda increases. Just give the denotations where the lambda is change in wavelength, wavelength, change in frequency, frequency. This is in hertz. Um, Actually, this is not just wavelength. Actual, actual frequency, actual wavelength. V is the speed of source or the star in meter per second, and C is speed of light. That's 3 into 10 to the power 8 meter per second. Finally, our fifth concept is the Hubble's law. Yeah. The Hubble's law states that V is proportional to D, where V is the speed of recession from an observer and D is the distance of the galaxy from the observer. So we can say V is equals to H naught D. H naught is Hubble's constant. So where V is equals to relative speed, D is equals to distance, and H naught is equals to Hubble's constant, which is 2.2 times 10 to the power minus 18 second for the universe. Okay, for the universe. All right. So that's all. This is the entire concept of astronomy and cosmology. With this, we are done with part 3 of the video. I will see you guys with medical physics and its concepts in video 4, I mean in part 4, inshallah. Bye.